talk is about architecture, right? So we're going to go way up into the clouds and talk about system design at a high level. There won't be any code. So if that makes you sad, now is a good time to go and to one of the other talks. Don't worry, I won't be mad. Also, none of the ideas I present are new, and they're not my ideas. They're just ideas that have been around for a long time, but for some reason not enough people know about them, hence this talk. Also, anybody who knows me knows that I have problems with my remote. Very strong opinions also. So, you have been warned, right? I'm opinionated on how to build systems, and I'm not afraid to share that opinion with others. I'm going to give you a little background on myself, so you have some context of where I'm coming from. I build stuff for a living. I worked in various industries, including business, sports, non-emergency health devices. Seriously messing with my remote. Great start. Non-emergency health devices, booking hotels, and booking flights. So, lots of different industries, pretty much always the same kind of MO. There was some big internet-based, highly available backend system, and then lots of distributed clients, right? Mobile, web, other kinds of devices. All these companies call themselves product companies, which is weird because some were B2B, some were B2C, solving different problems in different industries. Apparently, all you need to do to be a product company is to care about user experience. So I'm not a particular fan of the term. I like to think of them as information systems. An information system, as I define it, is you have this black box. Data comes in that's external from the system, right? Generated by users or other machines. You take this data and you store it securely, because if you lose it, you can't get it back. And then at some point in the future, a user comes along and asks us questions, and we give them answers, and insights, and intel, and so forth. Now, I want to get a feeling for the audience here. Who here has worked on an information system? Hands up. Everyone. Yeah, because if you haven't, you're building compilers, doing real-time embedded systems, or working on your PhD. Right? All of the systems we build are information systems. Who here has suffered technical debt? And felt the burden? Raise your hands. That's right. All of the exact same hands go up. I know, so don't lie to me. You've all suffered. Who here considers themselves object-oriented programmers? Okay, fair share. Any enlightened people in the audience? Functional programmers. Okay, a couple. For you, I have a question. Have you tried to teach your colleagues about the benefits of functional programming? Yeah, and failed miserably at it? Yeah, that's what I thought. This talk is a silver bullet, because it turns out that it solves both of those seemingly unrelated problems. Now, I know that makes me sound like a crazy person, but before you laugh me off the stage, let me also tell you that I believe in a conspiracy theory. And it goes like this. Model view controller, service-oriented architecture, don't repeat yourself, test-driven development. All suspiciously 3-letter acronyms, and all slowly but surely killing your projects. Right? These are poison. These are the snake oil salesmen of the software industry. Because they consistently overpromise, underdeliver, and give you this false sense of security that what you're building makes sense, until it's far too late to change it. Take, for example, encapsulation. What a beautiful idea, right? This is what I consider the complexity iceberg. Everything we build are essentially complexity icebergs, because this is how the real world works. In the real world, all your business domains are messy, they're difficult, they're complicated, they're complex. The way we deal with this reality is we split it up into multiple smaller problems. We solve those problems once, and then we sort of push it underneath the water, right? We build some API or facade up on top that we interact with on a daily basis. Because if we had to worry about all these details, we would go crazy. But the question is, how do these specific solutions attack this problem? Take, for example, MVC. Right? So you have this big, complicated system, and you're struggling with the complexity. So at some point, some consultants come in and they say, I know what your problem is. Your problem is that I see these things that look like models and these things that look like views. We need to separate this into different things. And so the consultants come in, they split apart your code base into a bunch of M's, V's, and C's. They pat themselves in the back and they go home. 6 months later, you're on the floor crying, because somehow the complexity didn't go away. It's still there. Now, I have horror stories about MVC, and you have horror stories about MVC. This talk is too short to tell them, but the reason I know everyone has suffered from this is because we invented service-oriented architectures, right? Service-oriented architectures were invented to solve that problem, that MVCs didn't. And how did they solve this problem? Well, those same consultants, they come back 2 years later. You're still struggling, so they say, no, I know what your real problem is. Your real problem is this: you have this big monolith. That's an MVC. We need to split this up into multiple services, right, that do one thing and one thing well. I mean, that sounds great. Let's do that. So we split it up. Now what happens? Well, now you had one problem and now you have four, right? And on top of that, you just created even more coupling in your system. I have never seen an implementation of this in practice, this architecture, where I can ask one of these services a question, and it doesn't need to start chatting to all the other services in order to give me a response, right? So it's just even slower because now you've introduced network latency. These were all some kind of weird technical solutions to what is essentially an architectural problem, right? They seemed like easy fixes at the time. We wanted a complexity iceberg, and all we got was a dependency iceberg, right? There was this huge oil spill, and then we just started pushing things underneath the water and hoping, God forbid, you never have to dive there and fix things. Same thing goes for duplication, right? Don't repeat yourself, deduplicate your code. You hear and see this everywhere. But Dry was never about duplication of code. It was about having a single source of truth. For every bit of information, there's supposed to be one place where we store that information. So we know all the things that depend on it, and we have that one place where we can change it. But this is not how Dry is done in practice. In practice, this is a sin committed especially by object-oriented programmers, is we create a bunch of abstract factories, abstract classes, inheritance trees, or even worse, we create mixins. We create mixins that create dependencies at runtime. You don't even see it in your static code analysis. We again attack an architectural problem with weird technical solutions, and all we get is more coupling in our system. Same thing can be said about reliability and testing. Because if you ask anybody out of the street, why do we test our system? The most likely answer is that we want reliable systems. Agreed? I like to think of it as confidence. I like to think of it as testing should give me confidence in my code base, that what I'm building works as expected, and that what I'm building makes sense. And that's what really irks me about test-driven development. Because these guys are really pro-unit testing, but if the purpose is confidence, why are we ignoring all these other things? You know, types and schemas are really useful. So are runtime assertions. Why is it that Erlang can do this really well and nobody else can? What about generative property testing? A lot of the times that we write unit tests for things that this would have been a better solution, right? Unit tests are easy, and that's why we write them. But if we want confidence, we need to go a step further. We need to think about how to build better systems. Not to mention just the coupling. Unit tests are terrible the way we write them in industry, right? I don't know why, but for some reason people are terrible at writing unit tests. The way we write them is all we do is we just duplicate code where whenever we need to change something, we end up changing the test in the code, right? That should be like a warning sign right there that something is wrong with this picture. Now, I know what you're going to say. You're going to say that I'm being just a little bit melodramatic, right? These are just tools. They're just tools that are supposed to help us write code. This is true. They're just tools. But people start treating them like religion. And the problem with religion is once you believe this, you can never change. You don't think of the fact that maybe there are better ways to build systems. Because if we're going to talk about religion, I need to tell you I'm a devout Rich Hickey convert, right? I believe in the almighty power of data and queues and the concurrency theory. Unfortunately, the concurrency theory isn't real, so all we've got left is data and queues, and that's all you need, by the way. So projects fail, they fail all the time. And I think they fail for one of three reasons. You don't understand the domain, so you build the wrong thing. You don't actually model the domain, so you build the wrong thing. Or inevitably, somewhere down the line, you break rules 1 or 2, and you're unwilling or unable to adapt and change. And that's when your project fails. So I've been doing some soul searching, right? I just said, there have to be better ways to build systems. And in order to figure out what is a better way to build the system, I said, I need to come up with some guiding principles. So I came up with 2. Whatever I do, I should strive to model the essence of things. I'm not promising myself or anyone that I will manage this. I am not that smart. But I will strive to model the essence of things. And I will try not to violate physics. So these are my guiding principles for architectural decisions. Whenever you come to a road where you need to decide, do I go down this road of architecture or this road? You go back to these 2 rules and see which one fits, right? So with that said, this is what I came up with. The /inspired recipe for success. This is all you need. You just need data, flow, magic sauce, and profit. Data. We need to set some rules. Data must be immutable. There, I said it. I want to give an entire talk about how immutability changes everything. But if I needed to summarize it in one slide, all of your data must be immutable because that's how the real world works. People are very simple creatures. They're simple-minded. They don't understand multiverse theory. They don't understand parallel universes. When I say that something is, it simply is. Nobody else goes and says it. Maybe it isn't, right? That's some form of schizophrenia. That essentially is what mutations are in your system. They're a schizophrenia, right? You do not want to go to users and tell them that they have Schrodinger data. The data sort of is and isn't there at the same time. Because your users will be very unhappy. On top of that, your developers will be very unhappy because they also don't understand the system, right? There's Schrodinger data in it. Avoid this at all costs. Switch to immutability. Data must be semantic. We're striving to model the essence of things, so we need to limit the kinds of things we have. And the way we're going to decide this is we're going to use semantics. If there are 2 things in my system, they must be different semantically. Because if they have the same semantics, they can be modeled by one thing, right? So we limit the number of primitives we use. But since we limit the number of primitives, we need to introduce recursion. Because recursion will now let us take these small amount of primitives and build big models. So this was really abstract. Let's talk about some concrete cases. Things that are primitives, for example, are scalars. Things like strings, numbers, booleans, nil, right? These are some basic things that have semantics that you would like to model a system with. It's really nice when you add the idea of identity into your modeling. I really like that Clojure has 2 different keywords for identity, symbol and keyword, because Clojure APIs really take advantage of this fact and apply custom semantics to each of these kinds of identities. You need collections, right? Things like lists, maps, vectors, sets. All have very different semantics, all provide recursion. And then sometimes you have custom stuff in your domain, right? Like this thing on the top is a string, but in fact it identifies in my domain. I want to give it the semantics that it's a unique identifier. So I just tag it with UID, right? And then whenever someone sees the string, they understand these additional semantics. Similarly, this thing on the bottom is not a string, it's a string representation of an instance of time, right? And so I pass this fact along through my system, and my system understands these custom semantics. So this is a way to provide custom semantics that are specific to your domain. And so that's data. Now we have flow. Flow is very simple. Flow must always flow, all data must flow in one direction. That's all you need to know, right? You have some data A, and you have some function f that transforms data A into data B. That's all you need to do. That's all you need to know. If you're more of a graphic person, it would look like this, right? You have A and B, and you have some function f. Notice that here we're saying that for all of A, f must have a B, but the reverse is not true. Not necessarily. We don't care because data flows in one direction. What Haskell and Clojure has taught me about system design is that it's very useful to fade away the functions. This is counterintuitive because it's called functional programming. Don't think about the functions. Just think about the data. This has 2 nice properties. First of all, when you start talking about the data that's flowing through the system, you have these very insightful conversations with your colleagues about what it is that you're modeling. And a lot of times, a lot of the problems that come out, they come out very quickly. And the second thing, and the second reason why this is useful is because people who are not classically functional programmers end up switching to functional programming. Because once they get excited about this idea of having data that's flowing through the system, it's they come to the realization on their own without you even telling them that functional programming is the way to go, because the functional programming just gives you this F to talk about A and B, right? And so we come to the magic cells. Your system is basically a black box. And the black box does two things. It takes facts and stores it in a log, and then at some point in the future, the user comes in and asks us questions, and we give them answers. Right? This is what we need to build. How do we do this? Well, first we'll need facts. Bruce Lee has a lot to teach us about system design. He once famously said, "You must be shapeless, formless like water. Water can drip, and it can crash." And I don't think he realized it at the time, but he was actually talking about flat data. Because flat data is like water. Flat data can take any shape you want. And specifically, I have a specific representation in mind, EAVT. Entity, attribute, value, time. It turns out that this is a wonderful representation of facts. Because it's flat, it can represent any kind of thing you have in your domain. You gotta trust me on this for now. It really can. And on top of it, it's something that everyone intuitively understands. And I'm not talking about programmers. Anybody you talk to will understand this representation. And the reason for that is that because it models very closely the way we think about the world. This table here, for example. As soon as I say this table has an identity, right? Entity, that first thing E, is just identity. It's something that everyone understands, but nobody can explain unless they're philosophy majors, right? Because when I say this table, everyone knows exactly what I'm talking about, right? This table has things on it, but for some reason we are automatically able to differentiate what is the table and what is on the table. This table also has certain attributes. It has a certain number of legs, it has a certain color, right? So those attributes have certain values at a specific point in time. If in the future I paint this table another color, it's going to have a new color. But it doesn't change the fact that at this point in time, this table had this color, right? Are you with me? Awesome. So this is a wonderful way to represent information, but it's not enough to represent communication, because communication is the transfer of knowledge. We need to add one more variable. We need to add this Boolean at the end that says, are we adding or retracting? Are we learning or unlearning information? And with this representation, we now have all we need. So let's look at a concrete example. Here we have a person named Bob. I arbitrarily chose to use integers for the entity IDs. This is completely arbitrary. It's just a reference to something in memory or in space, right? It's arbitrary. This entity has an attribute name, and the value is Bob. Notice I said person, but the model says nothing about people. Person is a semantic I apply to the system. It's from my domain. I define in my domain that things that are people have an attribute name. And the inverse is true. As soon as it has an attribute name, it's a person, right? These are custom semantics I apply to domain. The model itself does not implement this information. To be more specific, I learn about Bob at time 100, which is just a vector clock. And to be very pedantic, I learn about Bob, right? So that's a fact. What is a transaction? A transaction would look like this. You have a name, you have a person, Bob, and at the same time, notice 100, 100, we also learned that Bob likes cats. At some point in the future, we learned that Bob likes dogs, right, at time 111. If I were to ask you, what does Bob like? It would be a silly question. What does Bob like when? At time 105, we know that Bob likes cats. At time 111, Bob likes cats and dogs. Notice, a flat representation, but we can model collections. What if you want to model a constraint? What if you want to say, Bob can only like one thing at a time? Well, that's also simple. In that second transaction, we retract the old information while adding the new information, right? Cat no longer likes, there's that false there. Bob no longer likes cats, he only likes dogs. There's another nice thing we can model, which is relationships. Because there's no reason why the value can't be an entity that represents a different set of attributes. So here we have Bob and Mary. And here at time 111, we learned that Bob likes Mary. Notice it says nothing about the opposite, right? Maybe sometime in the future, Mary starts liking Bob as well. Another nice thing I want to point out is that since this is just a value to an entity, we can replace it with some way of finding that entity, right? If we say in our domain that names are unique, in the sense that if I have a name at value, I know which entity it responds to, I can just replace this, right? These are equivalent, isomorphic. So EAVT. Everything else I'm going to talk about depends on you understanding this. So if there are any questions about this representation, now would be a good time. What an intelligent audience I have. All right, we got facts. What now? Well, we need to store it somewhere, because if we don't store it, they're useless, right? We will store everything in a log. And more specifically, we will store it in an append-only log. And the reason is twofold. First of all, we want to model total order in the system. I don't care what you say about performance or all this other crap. For any response you have why total order doesn't make sense, I will have a counter response. You need to have total order in your system, because if you don't, nobody will understand what the system does. And the other reason is this. For some reason, we really care about our source code. We store it in a, wait for it, append-only Git repo. We distribute it to tons and tons of laptops, so we know it'll always be safe. We have linters, static code analyzers, all this other stuff. We really care about the quality of our code. What do we do with our business data? We store it in a mutating SQL database with last write wins semantics, right? We don't even know if there were other writes. The business data is the lifeblood of your company. You need to start treating it with respect. Put it in an append-only log. Now that we have this data stored somewhere, we need to ask you questions, because what's the point of storing it if we don't get any answers back? In theory, it's really simple. You have the entire log. So for any question, we can just go to the beginning of the log and start reading it. And we can answer any question we want, right? Because we have all the information. In practice, this is not really practical, because some queries just will take a really long time. This is why we invented databases and various kinds of caching, right? But there's no reason why we can't do that here. There's no reason why we can't build the system in such a way. We actually support multiple databases, each of them optimized for a certain kind of query. And the only trick is that all these databases are fed from that one log, right? So let's talk about questions and queries. What kind of questions do we ask our systems? And does our architecture support that? But before I do, I want to take a little tangent. Who here can read and understand SQL? Who here is asleep? You all can read SQL. Come on, don't lie to me. Who here understands data log? Awesome. Nobody. Which is why I wrote all my slides in data log. Because you really need to learn this thing. This, by the way, is data script, which is a implementation of data log written for JavaScript that will run in your browser. It is a wonderful tool. I actually use it in production. So, data log. It's as old as SQL, but apparently nobody knows about it. Let's talk about queries. One kind of question we ask our systems: auditing. Someone comes along and says at some point, I need to know who did what, when, where, and why. What do? Well, if you had a SQL database, you're screwed. You lost all of that data. There's nothing you can do. You can go home and look for another job. We, on the other hand, have the log. As soon as somebody asks this question, we can just hand them the entire log. They've got everything, right? They've got anything they need. So this one we got for free. Awesome. What about relational row queries? Right? This is the bread and butter of SQL databases. Given some ID, give me all of the values related to it. Well, in order to do this kind of query in an optimum fashion, we need to take the log and we need to create an index. Some kind of database that indexes by EAVT. Because we're interested in the ID and the attribute values that come with it. So as soon as we build this kind of index from that log, we can look at our first data log query. Let's go through this really slowly. Given a database and an ID, notice first of all that we pass in the database as an argument to the query. Immutable data, right? Given a database and an ID, let's find the actor name for that ID and the actor age for that ID. And then we just return it. So find is like select in SQL. Notice who here has done prologue, like in college, and failed the exam? Okay, a couple hands go up. Anybody understand logic programming, constraint solvers? Data log is a logic programming constraint solver. Basically, it says, by definition, it has all the data, and then each rule, these are rules, each rule you add limits the number of things that make sense for it, right? And I'll just keep doing backtracking, and it's a constraint solver. And anytime you have a question mark, that's a variable. And anytime that question mark is that same variable, like name and name, those two names must match, right? They're the same thing. And so you just introduce additional constraints until you get a set of results back. Does this vaguely seem understandable? Again, like nodding. Any questions? No? Okay. So don't worry so much about the syntax. I just want you to understand the ideas behind this. So relational column query. So this is where SQL databases usually fall down. If you give it too much data, you can no longer do averages, sums, and so forth, right? Because databases, they don't have the right indexes, so they have to do row scanning. But there's no reason why we can't just add a new index to our system. Specifically, we're going to index by AAVT, because once we index by attribute entity value time, we can now do those kind of queries in an optimal fashion. This is basically OLTP data warehousing, right, in your system. This says, given a database, I want you to find all of the entities that have actor age, and that's the age I'm interested in. Notice that here I'm saying I don't care about the ID because I'm interested in all of them. And then for that specific age you find, I want you to find the average of this, right? And because we've built that index, then this works blazingly fast.
I have a question.
Yes?
So this comes back as creating an index, or it's actually doing a query?
No, this is the query.
Okay.
So at some point,
Where did you create an index?
I'm not showing you code that's going to take a log and create an index. You have to sort of, you have to imagine this for yourself, right? You have a log of stream of data, and that's the result you want for each fact in the system, right? It's just taking that EAVT structure and then creating an index by that thing you want to introduce, right?
Is this supported by the tool that you're using? Or you're doing by yourself?
So this is an architecture talk. This data log is like SQL, right? So there are databases like Datomic that are implementing this as solutions, right? But this is more abstract, like in the sense that we can talk afterwards, we can talk offline. There are lots of nice tools that will actually give you this in production. But I want you just to understand that there are different kinds of questions we ask our system, and it's important when you choose an architecture to make sure you can answer all these kinds of questions, because otherwise you're screwed. Because another kind of question we often ask our system is graphs. We make graph queries all the time. You don't realize it though. Most of your business data is relationships and graphs, but because we usually use some SQL database, we have a really hard time with answering questions that are basically graph questions. But at an abstract level, if you want to ask a graph question, all you really need to do is you need to be able to traverse forward, which is an index we already saw, and you need to be able to traverse backwards. So if you have information, Bob likes Mary, you need to be able to answer very quickly two things. Bob likes who, and also who likes Mary. So you need to be able to traverse backwards. That's that second index. Once you have these two indexes, we have data log, and you can write this kind of query. This says, given a database and two actors, find me the actual actor entities, A1 and A2, in the system. For the first actor, find me all the movies he's played in. For the second actor, find me all the movies he's played in, but notice that the ends are the same. So this is saying, find me all of the actors, find me all of the movies that actor 2 has played in, that actor 1 has also played in, right? That's that constraint solver coming into action. And then once you have that M, just give me the movie title for all those M's. And just return the titles, right? So this says, find me all the titles where both of these actors played in. I didn't want to introduce a slightly longer example, but this is really easy to extend to N edges. So you can do full graph traversals very easily. Search. None of the indexes I showed up to this point have a good answer for search, for full text search, right? But we do have the technology, right? We have things like inverted terms to document frequency indexes. Things like Lucene, right, are running. So there's no reason why we can't just take a Lucene or like Elasticsearch, put it into our architecture, index it from that same log, and then ask it questions. And again, we see that data log comes to the rescue in that we have one place where we can talk about having a DSL for talking to this new database. Because this time it says, given that Lucene database in the query, I want you to do a full text operation in this database for this query, and then I want you to just return all the titles and scores so I can sort them correctly. I want you to pay particular attention to full text here, because here we're taking advantage of the fact that this is a different kind of identity, right? It's not a keyword, it's a symbol. And we're using that to our advantage in our data log to say, whenever you find symbols, that means these are custom operations on that database, right? Only Lucene knows what it means to do full text on itself. But notice that the data log syntax supports these kind of queries. So that's the ABT. I can go on and on. There's more kinds of interesting questions we ask our systems, which require different kinds of indices in order to build them. But the really important insight is that once you have this EABT structure as your source data, you can create all these indices. So that sort of comes slowly to a conclusion of this talk. What is all of this good for, right? First, I'm going to talk about the real world. If you get nothing else out of my talk, I want you to imprint this slide into your brain. Streams, trees, and mesh. All of your applications use these three data structures all of the time. All of the data coming into your system is a stream, which is very arbitrary, but as soon as it enters your system, it has become a ordered set, right? It has some specific order to it. It's a stream of data. All of your UIs, web, mobile, whatever, they're a hierarchy tree structure, right? That's what they are. But your business data, it's not a tree and it's not a stream. It's a mesh. It's a very specific kind of graph. And to give you an example of what I'm talking about, let's take Spotify, for example. So Spotify has, let's say, 3 core business objects. It has listeners, it has artists, and it has songs. When artists upload songs, they don't create a new kind of thing in our system. They create a relationship with metadata between artist and song. When a user listens to a song, it creates a new edge in our system with metadata because we keep track of how many times you listen to that song. When an artist creates an album, that's not a new thing in our system. That's a new relationship between that existing artist and song with metadata, right? And that specific metadata can have its own edges afterwards. Same thing with a playlist. A playlist is not something new in our system. As soon as Spotify introduced playlists, all they did was they took that user and that song and they created this new relationship between them. On top of that, once you have playlists, users can subscribe to playlists, users can subscribe to themselves, users can subscribe to artists. What happens over time is you realize that whatever your business domain is, there are only a couple core objects in it. And over time, as you expand your product, as you build it up, as you add features, what you're really doing is you're just adding a new relationship between existing things in your system. So this graph is becoming more and more and more dense. And that's why all of those service-oriented architectures and so forth, that's why they all fail. Because they fail to realize that the more stuff you add, the denser the graph becomes. So the sillier it is to try to distribute the data over the system. It makes sense to bring the data into one place. Streams, trees, and mesh. I don't care what architecture you decide to use, but whatever architecture you do end up using, you need to think about these 3 data structures. Does your architecture support constantly working in these 3 different dimensions at once? Because if not, you are in for a world of pain. So that's sort of the ROI on all this, is that this is one of few architectures that I'm aware of that actually answers this question of how to do this well, right? And people are using this in the industry and they're having really great success with it. I think this is one of very few architectures that actually give us a sensible answer to how to build complexity icebergs. So let's say I apply theory, because this was all theory, right? I want you to go home and actually do stuff with this information. Start thinking about queues. Your system is basically just a bunch of data traveling through a bunch of queues. The moment you start bringing those queues out, treating them as first-class citizens, a lot of nice properties start falling out. You know, as soon as you need to start talking about SLAs and performance and so forth, you need to bring the queues out. The sooner you do this, the better. I really recommend everyone learn data log, just so you understand the power of expression that's under your fingertips. This is an awesome website, learndatalogtoday.org. It's an interactive website where in about 3 hours with your favorite glass of scotch, you can learn all of data log. Nobody will tell me they can learn SQL in 3 hours, but you can learn data log in 3 hours. And also, really look into simulation and generative property testing. I think for a lot of the stuff we do, unit testing, simulation and generative property testing is a much better fit, which gives you much better results. And the nice thing is that once you start thinking about property testing from the beginning, you start designing systems in different ways. Because you start designing systems that are more testable using this kind of use case. And it turns out that once you do that, you realize that your systems have become a lot more decoupled. Right? They're just more maintainable over time. If you want to look at real life examples of how we use this architecture, LinkedIn is really well known for Lambda architecture. They're really proud of it. They have lots of talks about how they do things. Lambda architecture is basically this architecture applied at a macro level, like where their whole backend system is just a bunch of streaming data going to a log and then going through all these materialized views, right? Also check out Martin Putnam's talks about Samza and inverted databases. This is the same idea, but applied at a database level. So basically, how do you go from MySQL to something that actually makes sense? Also check out Datomic, especially the architecture. Even if you never use Datomic in production, or even try it out, look at the Datomic architecture, because these guys thought really long and hard about these problems. And they have some very keen insights about how they have a separate transactor, separate storage, and separated peers. And all of these systems close together build a database. But they're all independent of each other, and they all use EAVT as a communication protocol and synchronization layer. If you're more interested on the client side and building more user applications, check out OpenX architecture. Again, if you never use ClojureScript, it doesn't matter. The point is these guys have really thought about architectural problems, and the architecture really works nicely. And if you're more of the academic sort, I believe CRDTs are the future in the sense that they will give us some very nice answers to how to do, for example, multiple transactors while still keeping a total order in the system. And that's the end of my talk. Do you have any questions?
I have a question. Did I understand you apply those principles in your refactor code?
Yes and no. To some extent, yes.
Okay.
To some extent, and we are definitely moving forward and doing it more. So it's just a question of time.
Okay, so the follow-up question would be, you've mentioned all the good parts, so where are the dragons? Like, what do you would say as a drawback of using this approach?
Well, once you have an append-only log, and you have materialized views, and you have queues connecting these things, the hard truth comes out. Nothing is real time, right? Your systems aren't real time anyway, but this makes it explicit. So then it's a question of, what do you do, right? Where are the levers you want to pull? For example, you could say, I have a lot of incoming data, but most of the data is useless. Like, it's only useful for an hour. So I don't want to keep the entire history of my world. Fine. Take the append-only log, do it like Coffee does it. They have an append-only log, but then they have a compaction or compaction scheme, right? So again, there's a certain trade-off. If you want to store all the data, maybe you don't want to store all the data. There's a solution to that. Similarly, once the data comes in, it's going to take some amount of time to travel through the system to get to the database, right? So there's a lag between reading and writing. What if you say, I need read after write semantics? Like, you need to guarantee it, right? As soon as I write to the database, I need to be reading from it. Fine. You need to introduce a little more complexity into the system. before the log, put a database in, right? Put an ACID transaction database in that says, as soon as I read this, as soon as I write this, I can read this back in.
That's actually a good idea.
No, it's not a good idea. But in the sense it creates more complexity, but if you have a reason for doing this, like you have to just have write, if you tell me I must have read after write semantics, then by definition you need to introduce more complexity, right? So that introduces two things. First of all, it introduces another layer that you need to then push into the log and then go through your system. And your clients need to now be aware of two things. They need to be aware that most of the data is actually provided by this thing at the end. But then for those specific transactions that need to be read after write, we need to read from the beginning.
But this will screw your system at some point, right?
Yeah.
In the distributed system, you might actually put something to the database and lose it in the query, in the log, in the data log.
No, you can't. I mean, if your database is ASCII, then you don't, right?
Well, okay, you have transactions in the database size, but then you lose it in the event of the data log.
No. It'll just get there later.
But if it doesn't, it's a distributed system. It might not go to the data log.
Yeah, but okay, this is kind of my point. You're building a distributed system. If you can manage to put all this on one thing, if your application is that simple, then do that. Right? This is architecture we're building. We already assume we're distributed. So we're already solving all these problems. This just makes it more explicit where the dragons are. And it's your responsibility to figure out what the trade-offs are. Right? This is a really good example, for example, of Lambda architecture. Because Lambda architecture did that entire thing that I just said, but then they realized that sometimes we need to have a lot faster SLAs on certain kinds of actions. Like we need to be able to read it like that. They created something called the speed layer, which essentially they copied all of their business code a second time. So they created a lot more complexity, but they needed to do it because they had certain business cases that they needed to solve, right? So the point is, this is not like a cookie cutter solution. This is a framework for where you can decide where the dragons are and where you need to make trade-offs. Any other questions? I don't bite. I'm sorry if I start yelling. I'm just excited. Oh yeah.
How does integration with with external systems that are not following these principles? If you are going to integrate with a system which needs to be fetched in maybe some intervals or something, how do you write such a behaviors into this kind of architecture?
This is a very so the question is, how do we integrate this with systems that don't support this? The point is that this is a black box with very well-defined inputs and outputs. So if there are things that we need to add to the system, there's very nice hooks where you can add it, right?
So for example, you add the, timers as the external input and
you add external timers in. What is the problem you're trying to solve?
for example, fetching external data and synchronizing with external systems.
So fetching external data and synchronizing the systems. So there's facts that come through the log, and then you're building a materialized view, and you're saying, I need to fetch external data. You don't do that. The external data needs to go through that log, right?
Yeah, sure.
By definition, materialized views are just caches. So they don't do any fetching. I mean, in practice, if this becomes really complicated, you've got like an entire storm topology or something, it can do whatever it wants. But you need to realize that this is just transient data, right? All right, I guess we're done. All right, thank you.